ask questions. So, the lecture is about density functional theory. DFT, which is the method of choice used by chemists and condensed matter physicists to do calculations, and real-life calculations, when you want to know the state of the quantum system. Okay. So I'm going to explain to you what is the mathematical justification of this theory, what are all the questions, what are interesting problems, what has been done, and so on and so forth. And so there will be, so there are essentially two references for this talk. So the first is the famous paper by Lewin in '83. I think it's called Density Functionals for Coulomb Systems. You will very easily find it on the web. And then there is a more recent chapter that we wrote with Robert and Elliot. So it's a long chapter in a book which was edited by Eric Cancès and Guéron Friseke. So that's a Springer book. So our chapter is called Universal Functionals in DFT, I think. That's a Springer book that appeared last year. And there you will find essentially everything, although maybe not really explained the same as what I will do today. Okay, so the goal of DFT is really to replace the many-body Schrödinger equation by something that's easier to compute and still that gives good results. I mean, there's always a trade-off numerical difficulty and the quality of your approximation. Of course, you want the best approximation that costs as little as possible to be able to treat larger systems. And DFT, over the years, I suppose, as the best method. And so I'm going to tell you how DFT is formulated, what it means, and so on and so forth. And first, what I have to do is to remind you of Schrödinger's equation and explain to you why solving Schrödinger's equation is just too complicated. Okay, so let me discuss a little bit the complexity of the many-body Schrödinger equation. So what is it about? So I will be rather general. DFT is mainly for electrons in atoms and molecules or in solids, but the theory is actually much more general. It has nothing to do with Coulomb and so on and so forth. It also has nothing to do with quantum. It works perfectly for classical systems, okay, as Peter will explain on Friday. But of course, some of the approximations that work the best are for Coulomb, because people have worked for many, many years deriving these approximations. Anyway, so I'm really rather general, so I'm considering n quantum particles, identical quantum particles, in RD. D will be anything. I mean, later D will be 3, but so far D is anything. There will be an external potential V. That somehow describes the landscape or something. So V is really something that you, in your laboratory, impose to the system. So V is something that can be varied at your will. And we will assume that these particles, they interact with the two-body potential. So two-body interaction, W. Okay, we assume that it's a translation invariant, so it only depends on the relative, maybe just the distance, if you like. Okay, so let me give examples later, maybe. And then the equation, I'm going to neglect spin for the presentation. Okay, so there will be no spin. And so the equation you have to solve is the following n-body Schrödinger equation, which is so the sum j equal 1 to n of minus Laplace xj plus v of xj sum W of xk minus xk. Everything applied to psi is, say, e psi. Okay, so that's the real equation for it. Oh, lots of colors. Okay, so that's the main equation that we want to solve or to approximate. Okay, so there are of course two unknowns. The first is psi. So psi is a function of n variables, but this Sj is in Rd, so it's really a function of d times n variables. Okay, psi is assumed to be normalized in A2 of Rdn, because we think of psi squared as the probability distribution for these particles. And then we have to assume that psi is either symmetric or anti-symmetric. So symmetric for bosons, anti-symmetric for fermions. Okay, now you see that it's really an eigenvalue problem. So the other unknown is E, of course. The energy of your system. And you see that the operator that's on the left, the Hamiltonian, is actually invariant under changing the labels of the particles. So this Hamiltonian commutes with permutations, and it can be restricted to either the symmetric or anti-symmetric subspace. And so you're just solving an eigenvalue problem either in the symmetric or the anti-symmetric subspace. Okay, so I will always use the notation L2A or S Rdn, where this means either an anti-symmetric or symmetric. And then there is the E, okay, so E is the unknown eigenvalue, of course, and in this talk we will not really look at excited states. Well, actually we are, because if you look at fermions, it's a kind of excited state for the full Hamiltonian, in a way. Okay, but E, we will always look at the ground state. And ground state just means that you look at the lowest possible eigenvalue. Okay, so lowest eigenvalue. Of course, in the corresponding symmetric or anti-symmetric subspace. So if you like, E is really the minimum of the spectrum of the big operator H n of V, either in the symmetric or the anti-symmetric subspace, and this guy I call H n of V. I do not put W in the notation because W is the interaction potential between my particles. It's kind of fixed, it depends on the particles. But V is what we typically does. So examples. So the first example you've seen in the last hour, in the talk by Philip. So if you look at n electrons in a molecule, okay, so in this case, of course, D is equal to 3, W is the Coulomb potential. So in some units, you can just take 1 over the distance. Usually, chemists, they put a half here, okay, which are atomic units, but I'm not going to put this half for simplicity. I should, but. And then V, of course, they are fermions. And then V is just the potential that's generated by the nuclei in your system. Okay, so that's minus the sum of the Ck x minus Rk K equal M. So for instance, if you want to describe the water molecule, so there is water, so there's 1 oxygen and then 2 hydrogens. There they are. Okay, so you have 3 nuclei. So there is Z1, which is 8, there is Z2, which is 1, Z3, which is 1. Okay, you have 1 oxygen and then 2 hydrogens. And N is equal to 10 for the water molecule. You see, if you want to describe the water molecule, you can always assume it lives in a plane. And so you have only 3 variables, which are these 2 lengths. Right, so here I call it L prime, maybe I call it L prime, and this angle theta. And what the chemists want to do, what they want to do is to find the shape of water. What's the optimal shape? Meaning what are the values of L prime, and theta? And for this, what you do is you minimize over all possible variables in your system. So you have to minimize over the electrons. First find the optimal state of the electrons, and once you found the optimal state of the electrons, you have to minimize over where you put the nuclei. Okay, so, and when you do that, you should not forget to add the nuclear repulsion. So you would typically look at the function which from R1, M gives you the E, N of V. So I'm going to, instead of calling it E, I'm going to call it E, N of V. Maybe with square brackets. Okay, so that's an important notation. So E, N of V is what's going to be E, and that's the lowest energy. And in the case of molecules, then you should, of course, add the nuclear repulsion. And you look at this as a function of the RKs, and then you minimize, and you will find the optimal shape of your molecule. Okay, so if you do it for water, then you have 3, of course here is R1, here is R2, here is R3. And by symmetry, you can always assume R1 is 0, and then so on and so forth. If you minimize, then you will, you're supposed to find the shape of water. So this is about 1 angstrom, and then the angle is about 104 degrees for water. And of course, what chemists want to do is to compute the shape of molecules, compute what is happening close to the minimum, so they also want to compute the Hessian. If you compute the Hessian, that will tell you the vibration modes of the molecules. Okay, so you know water has 3 vibration modes, because it can vibrate like this, it can vibrate like this, or it can vibrate like this. And these vibration modes are very important in practice. And then, of course, water is not so interesting because we know water very well. What chemists want to do is to study very complicated molecules, see if they can predict some kind of chemical reaction that could happen, what's the shape, and so on and so forth. That's used to find a new medication, for instance. It's also used for big systems to optimize properties of material. Okay, so like production properties. So people would want to be able to predict on a computer what's going to be the behavior of either your molecule or your material in order to avoid doing too much experiments, because that's very costly. In the end, they eventually do the experiments, but they try to do the computation on the computer first to see where to go, and then be sure that they do the experiments once they know what kind of experiment they want to do. Okay, so this is really used everywhere, and of course very important. Let me discuss now the non-interacting case, because that's very important. So the non-interacting case is when I have no W. So what is happening in the non-interacting case is very easy. Well, so you will have a difference whether you look at bosons or fermions. The picture is always like that, so I have to look at the spectrum of minus Laplace plus V in in L2 of RT. Okay, I look at the one particle problem. So I look at minus Laplace plus V. You see the Hamiltonian, this term is not here, and then I have the sum J1 to N of minus Laplace plus V acting in all the variables. So I have to look at minus Laplace plus V. It has some, so let's assume there are some eigenvalues. So there's a lambda 1, lambda 2, and maybe this guy is degenerate, so let's say it's lambda 3, lambda 4. Typically, there will be essential spectrum, something like that. Okay. And then the plane, which is really just an exercise, is really the fact that for bosons, when you compute En of V, when W is 0, what is it that you find? Just to see if you're sleeping. Yes, you find N times the lambda 1 of, say, minus Laplace plus V. Okay, so the picture is that for bosons, you're going to you're going to put all your N particles in the lowest energy state. That's the good guys bosons. And the psi will be, if you like, let me call U1 the corresponding eigenfunction, and it would be U1 of x1, U1 of xn, which is just U1 tensor of x1, xn. Okay, so it's an exact Bose-Einstein condensate, if you like. And then for fermions, this was mentioned by Jan Philipp quickly. For fermions, I mean, you can't put them in the same state because psi is antisymmetric. So what you will do is you will just populate the eigenvalues. So here I can put two guys. So you populate the eigenvalues one after another. So E and P will be the sum of lambda J minus Laplace plus V. J equal 1 to N. And the psi will be a Slater determinant. Let me explain what that is, but let me write it's U1 tensor UN. So how do you prove this, or how do you see this? I mean, let's assume, for simplicity, so assume that V is a confining potential, so that the spectrum is purely discrete. Okay, then you can work in the basis of eigenfunctions. It's easier. Okay, so then you have the basis of eigenfunctions, Uj satisfying this. Okay, so they are orthonormal. Another main point is that you can read the basis of the n particle space. So the Uj1 of x1, Ujn of xn, which is Uj1 tensor Ujn of x1 xn, when J1 and Jn take any value, and that's an orthonormal basis of L2 of Rd to the n. So we've got basis for L2 of Rd to the n. And of course, we don't work in the full space, we work in either symmetric or anti-symmetric functions. And that's easy because you can just take these products and then symmetrize them or anti-symmetrize them, which is just applying the projection onto a symmetric or anti-symmetric. Okay, so what's the definition of U? Well, let me just define it with, well, okay, Uj1, Ujn with a tensor like this. Right? So usually one puts the 1 over square root n factorial. And then what you do is just you anti-symmetrize your product. So it's just the sum of all computations of Uj1 of x sigma of 1. And I forgot the sign of the computation, Ujn of x sigma of n. Okay, which is really just the Slater determinant of the Ujk of xn. that's what's called a Slater determinant. So if you like, it's the easiest, the simplest symmetric function that you can build. You need at least n functions. That's a Slater determinant. And now these guys, so U, J1, wedge, U, J, n, they also make up a Hilbert basis of the L2A of Rd to the n. And of course, you have to require that you can order the indices if you like. So J1 should be less than J2, should be less than Jn. Okay, and now when you compute your n-body Hamiltonian in this basis, you see it's diagonalized. So when you compute the H n of V, right, which is applied to U, J1, H, U, Jn, that's really just the sum J equal 1 to n minus Laplace plus V in the variable J, applied to the same gap. If you do the computation, you will see it's the same as taking this operator and applying it to any of the functions in the wedge. And so you find the sum J equal 1 to n of the lambda, maybe I should call it K. Lambda Jk times J1, Jn. Okay, so once you've diagonalized your one-body operator, you've diagonalized the n-body operator. The eigenvalues are the sum of the eigenvalues, and the lowest you can get is when you take the sum of the n lowest. And that's the reason for this formula. But of course, we know more because we can diagonalize the full operator. And it works also if you have continuous spectrum, just use the spectral theorem. It's similar. And for bosons, it's similar, except, of course, that you have to symmetrize instead of anti-symmetrizing. And then somehow it's not so easy to get an orthonormal basis because it will depend on how many times each function is repeated. But let's not go into this, it's just similar. Okay, so I'm sure many of you know this very well, but imagine that now you want to discretize your Schrödinger equation. I mean the n-body. Now I'm not assuming that W is 0 anymore. So how do you discretize this n-body problem? So the usual way would be to first you pick an approximation basis of the one particle space. You take some chi1, chi b, okay, some basis, I mean not basis, but orthonormal system. Let's assume it's orthonormal for simplicity. In L2 of Rd. Okay, you can think of finite element or something. Okay. And B is the number of functions in your discretization basis. And then once you have this guy, you automatically get a discretization basis in L2 of Rd to the n. Just by taking these tensor products. So in the family case, you just take those tensor products, and in the bosonic case, you take the symmetrized tensor products. Okay, and then you are in finite dimension, and you have to just find the eigenvalue of a matrix. Okay, so then eigenvalue. Well, you want to find the lowest eigenvalue of a big matrix. Is this doable? The answer is no. Why? In practice, it's not doable. Why? Because if we start counting how many functions we will have, then it gets very easily crazy. Okay? So you see that we have n functions, and then we put everything to a power n. will have of the order, so we will work essentially in dimension nb to the power n. Not quite, of course, because you have to take into account symmetry and anti-symmetry, but I mean, this will only affect the prefactor. And typically, NB is at least n. Actually, for fermions, NB has to be at least n, otherwise you cannot build sufficiently many functions. Okay, so typically, I mean, you have to think that NB is your discretization basis for one electron, so I mean, it cannot be too small. So typically, NB is much larger than n, or maybe NB is of the order of a huge constant times n. And so you are even, so you have of the order of n to the n and then you have to build a huge matrix. Okay? So huge matrix. Okay, which is an order nb to the n times nb to the n, and which you're supposed to, you don't quite diagonalize it, you only want to find the lowest eigenvalue, but still, it's crazy. So for instance, for water, so if you imagine that NB is 10, or maybe you say NB is 100, right? So each electron I discretize over 10 functions. So, then you see that you end up working in dimension 10 to the 20, because you have 10 electrons. And so it's just not doable. So there's, it's definitely not doable. This method, which nobody uses because it's not doable even for water, is what chemists call full CI. CI means configuration interaction. And what does it mean? So it means that you look for upside of the following form: C, J1, Jn, and then Chi, J1, say for fermions, Chi, Jn. Okay? Of that form where the Jk's are between 1 and B. And then the unknowns are these coefficients. And the coefficients are what's so that's this big matrix, if you like, or that's the psi, and you're trying to find, so you're just assuming that your psi is of that form. And this is definitely not doable. Of course, when W is 0, it's much easier. So if W is non-zero for us, but if W is 0, then it's much easier. So for bosons, you only have one function. Okay, so you have essentially NB unknown, because you only have to find the lowest eigenfunction of minus Laplace plus V. I mean, still, it could be that you have NB unknown. And for fermions, you have of the order of n times NB unknown. Right, because you have to find n functions, each of them being discretized over a space of dimension NB. It's still quite big, I mean it's big, but it's polynomial at least. Not exponential. Okay? So of course the non-interacting case is much easier than the interacting case, and the full idea of DFT is to try to replace the non-interacting problem by the interacting problem by a non-interacting problem. That's the main idea, just to go into this much lower complexity. This I will explain later. But before, let me make some comments about low-rank approximations. Okay, so you see, so for bosons, actually, you know you can only pick one function, so one phi, that you write the sum of ck and kk. In a way, it's a low rank because it's rank 1. Of course, you work in dimension NB, but you're looking only for one function. So it's rank 1. And for fermions, the best you can do is to do rank n, meaning that you look at n functions, okay, that you expand over your basis of nb. Okay, so you have uj, which you write as a sum of c, j, k, k, okay, where j is from 1 to n and k is from 1 to nb. And when you're doing that, then you're really assuming that your psi is a Slater determinant. So you assume that psi is a Slater, but you don't know the functions, the orthonormal functions. You try to find, and then you optimize. So when you optimize over the C's, then what you're doing is you're assuming that your psi is a Slater. So this is Hartree-Fock. Okay? And so in chemistry, of course, Hartree-Fock is not precise enough, so what people do, when you say low rank, so they would say, well, maybe psi is not 1 Slater, but maybe 2 or 3 Slaters. Okay, so you can assume that psi is a, say, finite sum of some UJs. So, maybe I write just names, so finite sum of some determinants with from U1 UK. So now you have a new parameter k, which is the rank of your approximation, and each uj now is expanded over your basis. Okay? So if k is on order n, somehow it's not much more crazy than Hartree-Fock. And this is what they usually do in practice. So let me give you some examples. So let's look at water again. And now let me tell you what you find when you do actual computations. Okay, so I'm going to discuss the angle theta and the length L of the two bonds. And the two lengths are going to be the same. Okay, so what is the experimental value? So the experimental value for L, which is the length of this is 0.9584 Einstein. Okay, and then what's the angle? Theta is 104.48 degrees. That's the experimental value. Now, let me tell you what you get when you do Hartree-Fock. So when you do Hartree-Fock, it's not, it's not bad, but it's not really good. So you get 0, sorry, I will tell you in which basis, but later. So you get 0, 93, 95, and 106, 22. So you see the length are a little bit smaller, and then the angle is a little bit larger. Chemists are not happy, so for them it's a very bad result. So to compute this thing, I use a software which is called ISTA. And I use a basis that's called C, C, P, V, Q, Z, which has NP equal to 150. Okay, so let me remind you that water has 10 electrons. So I'm using a basis of essentially 100 functions. And the chi's, so these are the chi's, right? The chi's are Gaussians times polynomial centered at the 3 nuclei. So you have 2 hydrogens. So you put a Gaussian times polynomial, Gaussian times. So I don't remember how many at each side. Of course, oxygen has more functions than the 2 hydrogens. I think hydrogen has about maybe 10 functions, but then oxygen much more. Okay? And then you optimize for Hartree-Fock, you find these numbers. Now let me, and doing this on my computer took about 20 seconds. Let me tell you what you find with the best method used by chemists, which is called coupled cluster. I'm not going to explain what this is, but it's a way to do a low-rank approximation. So you start with Hartree-Fock, and then you generate a finite number of determinants, some excitations that you write in the form of an exponential. Not too many. Actually, they only have single, double, and a few triple excitations. Okay, so you can count how many determinants you get. Still, it's a big computation. It took about 10 minutes on my computer. So much, much longer, which is not reasonable, but the result is good, right? So you get 0.9536 and 14454. So you see that it really seems that solving Schrödinger really gives you the true numbers of nature. Even though we've made some approximations, right? We decided that the nuclei don't move, and that they are classical. And it's not a big basis. So actually, if you refine the basis, you will find even better, and you will be even closer to the experiment. So this is telling you that you can really get extremely good results if you are able to solve the equation. You cannot really solve the Schrödinger's equation exactly. Full CI is just undoable because you have to work in dimension 10 to the 20. Actually, I pressed the button and then I run this on the cluster of my lab, and it was not complete. It was computing for several days. I thought maybe after a while it would manage to get something. But then the whole cluster crashed. And so, yeah, so you definitely cannot do anything. Maybe with a very big cluster, so, yeah. Maybe you can do it. Anyway. Yes?
I'm not sure I understood how you typically choose this
NB, and then we want NB to be not too large, but I mean, now it's chemistry. Right? So the first question is how do you choose the chi-J's? Then how many you put? Maybe the next. Okay, so there was this discovery by John Popper that if you take Gaussians times polynomials, then you can easily compute all the matrices that you need to compute. So you have to compute some kind of loss of Coulomb integrals, and you can compute them exactly extremely fast. So this is why they always use Gaussians times polynomial. This was discovered by Popper. He got the Nobel Prize for that. Okay. And the most well-known software in quantum chemistry is called Gaussian. That's the reason. Okay, so the chi-J's are just Gaussians that you place. So each nuclei will have a finite number of Gaussians times polynomial. These Gaussians times polynomial, they've been optimized already for you. So when you say I want the basis C, P, E, Q, Z, then you get some Gaussians times polynomial. So there is a certain list of such functions for each atom of the periodic table. Okay, with some coefficients. And they've been optimized by chemists, okay, to make sure that they work very well if I just compute H alone or if I just compute O alone. Okay, so somehow the spirit is that you want to put as few as possible. So NB should be as small as possible, and the way chemists do is really they optimize the basis so that it works well for an isolated atom. So they take Gaussian times polynomial, and then they optimize, they fit the parameter to experiments, if you like. And then they use this basis in a molecule where you have several atoms together. Okay, but I mean, it's a little bit of cuisine in a way. So over the years, they managed to find very efficient ways of, I mean, it's amazing that you can get so close to experiments with such a small basis. If you would do finite elements, typically you would put much, much more chi-J's. But here you have very few because they've been optimized to work for isolated systems.
Can I also ask
yes.
the times you quote, this is actually for minimizing over psi and over the...
Yes. Exactly.
So how many iterations do you need to find?
Not so many, like 5 or 6. So even the well, I have to tell you what was the starting point. Okay, so I had to choose a starting point, so I've put 1 angstrom and 90 degrees. Okay, it's not so far from the true guy. Okay, but so then you only have to optimize the length and the angle, and I think it was only about 4 steps, 4 or 5 steps. Okay, so you have to minimize your electronic problem about 5 times. And then you have to compute the gradient with respect to the nuclear position, which takes some time. And then you do a kind of gradient descent or something. Newton problem. Okay, now this lecture is about DFT, so I can't resist telling you what I got using DFT. Okay, so then I use DFT. I mean, DFT doesn't mean anything because there are thousands of functionals, but I use the most famous one, which is called B3lib. I will get back to it. And then it took 20 seconds again, because DFT is in spirit very close to half structure, but much better. Okay, so it's on the same order of with respect to computer time, okay, but much better results. And I got 0.9605 and here 10488. Okay, so you see, the spirit of DFT is that most often you will get very good results at a quite low price. And that's usually, I mean, when it's a very big molecule, that's the best you can hope. And if it's a molecule for which you think you could run more precise calculations, you first do DFT, try to understand what's happening, and then in the end, once things get a little bit clearer, maybe you run a very expensive calculation to finish your study. So DFT, now, where is the eraser? Oh, it's on. Back here. Oh, I have to. Okay, very good. So DFT is a very old subject which had 3 main periods. The first period was around the 20s or 30s, which was essentially around Thomas Fermi. Okay, so this was the period where people invented, even maybe Schrödinger's equation was not so clear. And so they invented simpler functionals, and Jan Philipp is going to discuss Thomas Fermi at length. That's the simplest DFT, it's from the 20s. Okay? Then there was a big revolution around the 60s where people realized that there was a way of approximating the many-dimensional equation by the non-interactive problem. And these were the works by Owen, Berg, and Chan around 64, or something like that. But at the time, they could not really do good computations. So it was pure theory, in a way. They did some computations, but they were not precise enough, the results were not so good. So that was actually the real first revolution of DFT. And then the third period was the one in the 90s, or end of the 80s and 90s, where suddenly they understood how, so first they had the computer capability, so they could actually compute, and they understood how to come up with good models. Okay, and then there was a really huge revolution at the time. So to give you a little hint about this revolution, so I mentioned the functional B3lib. So that's one functional very famous in DFT. It's the one that's used the most by chemists. The acronym is so the B is big. The 3 is because it's based on a functional that has 3 parameters. And I think it's a paper from 1993. And LYP is Li-Yang-Ka. It's also a paper. I have the reference somewhere. I don't remember the year, but it's 90-something. Let me tell you. Oh, no, it's 88. It's the most famous functional. Now I want to give you an idea I did a research on Google Scholar, and I found out that it has more than 350,000 citations in Google Scholar. I mean the functional, not the papers, the functional itself. So this really appears in more than 350,000 citations, and it appears in more than 40,000 patents. Just to give you a hint of the huge impact of this discovery. And in these 40,000 patents, 1,000 is just for sensor. So it's just to optimize all the technology in your phone or computer or TV. Anyway, so that's the result of this big revolution from the 90s. So now I'm going to describe very vaguely to you the general spirit. When did we start with it? Oh yes.
So then I asked, how close was the simulation, or how close is the result of the simulation to the true DFT itself? And you could exactly minimize.
Can you repeat the question?
Okay, so you did a simulation with the DFT model, right? And there's also
Yes.
a message problem. Good.
Yes.
And how close is your simulated result to the true result of the
What's the truth?
The
DFT
right?
true?
Yeah.
The exact minimum for that function. You mean if I vary the basis?
Yeah, exactly.
I don't know. It's a good question. I mean, it will not be the experiment, because it's still a matter of time. So you have an exact model. I mean, experiment is not Schrödinger, by the way, because the electrons are relativistic, they should not matter so much, the nuclei move. So even Schrödinger is an approximation. Then we do DFT, we do an approximation. I'm going to explain to you today and tomorrow that DFT is in principle exact, except that in life you do approximations. And then of course there is the basis implication. And then there's another problem that maybe you're not at the minimum in your basis, which is an algorithmic problem. So all these things pile up, and then in the end you don't quite know where the error comes from. Okay? When did we start? And when we have to...
We started about 10 minutes late, so that we still have like half an hour.
Okay, so I have to stop at 40, so at most. Very good. So now I'm going to explain to you the main idea of DFT, and we will prove theorems later. And by the way, what I will tell you, we don't know how to prove anything for what I will tell you. But that's what people wanted to do. If you know how to prove something, tell me. So here is the spirit. So let me remind you that we have this Schrödinger problem. Minus Laplace plus V less J plus the sum W raised J minus XK psi. Oh, maybe I put everything on one background because that's quantile equal to E and V psi. This is Schrödinger. Okay? That's our goal. So the idea is that we're going to replace it by a non-interacting problem. So we won't solve this. We will instead solve the sum of, or we want to solve minus Laplace plus V tilde h j psi j well, psi tilde is E and tilde of V tilde psi tilde. Okay, that's a non-interacting problem. And now we want the non-interacting problem to represent correctly the true interacting problem. What does that mean? Well, so one thing we could do first is to ask that the energies are the same. Okay? So let's put the constraint, if you like, that E n of V is equal to E n of V tilde. And of course, remember that here, for bosons, it's completely trivial. Because the equation I'm solving is really just minus Laplace plus V tilde phi is E tilde n of V divided by n phi. I have only one equation for bosons, as I explained to you. But for fermions, I have n equations. solving minus Laplace, because d tilde uj is equal to lambda j uj, and then d tilde is the sum of the lambda j's. Okay? Good. So first thing we do, we say, let's assume we want the two models to be the same. We will be looking for v tilde. It's an inverse problem. We will try to find or show that there is, and we will fail, but we want to know if there exists a v tilde so that the non-interacting problem behaves the same as the interacting problem. And so first thing to do, let's ask the energies to be the same. This is completely trivial. If we do that, why? It's completely trivial because, yes.
We just add some constants.
Exactly. Yes, so if I add a constant to V, then the energy is just shifted by n times this constant. Okay, so I can always assume that they are equal just by shifting V tilde, whatever it is. Okay, so there's nothing. If I just assume the energies to be the same, I didn't do anything. So we need more. We can always assume they are the same, if we like. We can always assume they are zero, even, if we like. Okay? So that's in a sense, that's easy. But it doesn't contain any information because V is always defined to a constant. So if I add a constant, then the En, maybe I should write this somewhere. Okay. So the En of V plus constant is equal to En of V plus C times N, and same for the tilde. And so I can of course always pick the constant to make them equal. Okay, so then, so this did not quite work, so then we will just go to the next step and assume that the derivatives are the same. Okay, derivative in V. Okay, so imagine I have a potential V, and I have a potential V tilde, and I assume that if I move V a little bit, then the other guy should move the same. So what is the derivative? Well, maybe the derivative exists when it's not degenerate. So maybe we assume it's not degenerate for simplicity. So assume En of V has a multiplicity 1. Which, by the way, is always true for bosons, for reasonable V and reasonable W, by Perron-Frobenius. But for Fermat, we don't know. And I guess sometimes it's just wrong. But let's assume, okay, let's assume that it has multiplicity 1. Then, when you perturb V a little bit, you can compute, just by Feynman-Hellman or just perturbation theory, what's the next order. Okay, so if I compute En of V plus T W, and then I do an expansion in W, and then I will find that it's En of V plus T, and then I will see rho times W plus little rho of T, where rho is the density of the ground state. So this was defined by Jan Philipp, but let me explain it again. So let me assume that psi is the ground state. Okay? And then when I compute, so of course I have that En of V is psi, and then I am common psi, and which is just psi and then Hn of 0, psi plus psi, and then the sum V of xj psi. And so you see that the term that depends on V is an easy term because it's really a one-body term. So when I compute, so I have to compute this term. What is this term? It's really the sum of V of xj times psi squared of x1 xn dx1 dxn, so j equal 1 to n, but psi is either symmetric or anti-symmetric, so psi squared is symmetric, and so all the terms in this sum are the same. And so I get n times v of x1, for instance, psi of x1 xn, squared xn. And so that brings the density. So of course that's a very important object because it's density functional theory, so that's the main object of the talk. So the rho psi of x is n times the psi of x and then x2 xn square dx2 dxn. That's the density. The density is a kind of a classical object because it tells you the local number of electrons in average, if you like. It's also just the one marginal, and then multiplied by n. So it tells you how many electrons you have in average in a given region of space. It's a purely classical thing because it only involves psi square, which is a probability measure. So that's the density, and this is what appears here, right? Where psi is the ground state. Okay, so asking that the derivatives are the same is telling you that the rho of psi must be equal to the rho of psi theta. Maybe I'll put it here. So you see, you assume that they have the same rho. So the rho of psi theta is equal to the rho of psi. This is the constraint we will put. So maybe I summarize. You take a potential V, you compute the ground state psi, where you can't, but imagine you can. You compute the ground state psi, then you compute the density rho psi. And then you ask yourself, now it's a pure inverse problem. You ask yourself, is there a potential V theta such that the non-interacting problem, the ground state, psi theta, would have exactly that rho? And then I've replaced my interacting problem by a non-interacting problem. And so I have to think that my V theta is a very complicated function of V. I don't quite know what it is. In the end, we will do approximations. But I think that V theta is a very complicated function of V, if it's possible to find V theta. So that's the spirit of DFT. So let me mention that so if En of V is degenerate, and maybe E theta also. So when I look at En of V plus Tw, actually because it's concave, there is always a right and a left derivative in V. Okay, so you can see that d over dt and T, so that's equal. So you will see that it's equal to the, so now we'll mess up, but I think it's the inf. Is it the inf? Yes. I think it's the inf over psi ground state of the integral of rho psi times W when T is 0 plus. Okay, so I will come from the right side. Feynman-Hellman will tell you that you have to optimize, you have to look at all ground states. They all have a certain density rho, and that's the right derivative. Okay, and then the left derivative is the sup, which is the mean and the max practice. Anyway, so of course, when it's degenerate, then you have several densities, and then this scheme is not so clear. But chemists, I mean, they don't care so much. I mean, they know, right? But so when this guy is degenerate, I have several densities. If this guy is degenerate, I have several densities. Then it's not so clear where I ask that they have one in common, or they have all in common. I don't know. But let's not worry. Let's assume it's degenerate, if you like. Anyway, so the main idea is you try to describe your interacting system by a non-interacting system, and it's an inverse problem. You're trying to find a potential V theta that reproduces the density of an interacting ground state. So let me state a theorem to finish for today. It's a theorem that tells you that if everything is nice, then V theta, if it exists, is actually unique. So let me put as assumption. So let me assume that T and W and V theta. So I'm assuming that V theta exists. And I'm not discussing, I will assume it's non-degenerate also for simplicity. And I assume that they are in LP plus L infinity, and I put the usual assumptions to make sure that the energy is well defined in H1, which are T equal to 1 in dimension 1, so T the other one in dimension 2, and equal to 0, 2 in dimension 3 and higher. This is what works for LP spaces with respect to H1. Okay, so that's the assumption that we make the energy well defined in H1. And let me, for fermions, assume that it's non-degenerate. Then, V theta is unique. I should say unique up to a constant, but the constant is fixed by this condition. So then it's unique. This is a version of what's called the Lewin theorem. But it's an easier Lewin theorem because, as you will see, it's only about the non-interacting problem. So I'm going to do the proof and then I will stop. So the usual one that you will find in the literature involves, I mean, we will very soon get rid of W and only discuss the non-interacting problem. So it's Lewin for the non-interacting problem. And the usual Lewin is more complicated. And in particular, it uses a unique continuation. So it relies on unique continuation for the n-body problem, which is not fully understood. So I have a student, Louis Garrigue, who proved a unique continuation for the n-body problem, but he could still not get the optimal conditions on the potential. And in particular, not the ones I mentioned here. But if you look at the original problem, namely what's written there, you actually don't need anything, because I'm not going to use unique continuation, I'm going to use Perron-Frobenius, which is a little bit unique continuation, but he doesn't. Anyway, let me do the proof. So I'm going to use Perron-Frobenius, so I'm going to use the fact that the lowest eigenvalue is always non-degenerate. But when I'm in the full space. Okay, so I'm going to use that the lambda 1 of minus Laplace plus V is non-degenerate under this assumption with a strictly positive eigenfunction U1. Sorry, I will use it for theta, of course. Okay, so when V theta is in those LPs, then it's known that if there is, we assume these eigenfunctions exist, of course. And I'm going also to use that the En of V is also non-degenerate for bosons, for the many-body bosonic case. And for fermions, I assume it's non-degenerate. Okay. So what's the situation? So in both cases, I know that the En of V is non-degenerate, so they are signs unique up to a phase. And what I'm doing here, I'm looking at the density of psi. Okay? And so I know what it is, there's a rho, so I'm calling rho, that's the rho psi. Then I have no question. Sorry, maybe it's not so clear what I'm saying, but I told you before, if one of the two is degenerate, then it's not so clear what we require. So if we require that they coincide for one density, then I may have the problem that 2 two v tilde do not coincide for the same density, and then I don't know what to do. So when I assume that it's non-degenerate, I know I have only one density and I don't have to worry.
Sorry.
Oh, yes?
Just a question. Number one of minus Laplacian plus VT, the non-degenerate with what you want to say?
With a positive eigenfunction.
The
U1.
positive.
Okay? Positive in the sense that U is non-negative, and the set where U is 0 has 0 measure. That's the best I can say under these assumptions. Very good. So now we assume we have a V tilde 1, which gives me a psi tilde 1, which gives me a rho psi tilde 1, which is rho. And we assume we have a V tilde 2, giving me the psi tilde 2, and giving me the same rho. And we want to show that necessarily V tilde 1 is equal to V tilde 2. And let's assume that En of V is equal to En of V tilde 1 is equal to En of V tilde 2 is 0, for instance. This we can always assume. Very good. For bosons, it's obvious. Because for bosons, I told you already, okay, so I look at minus Laplace plus V tilde 1 phi 1 equal to 0. Okay. And what's the corresponding density? So I know that rho is n times phi 1 squared. Okay. So rho I know because it's given, and so I know phi 1 squared. That's okay. So here I have 1 or 2, of course. I have 2 guys. So, right, you know. Okay, so I look at V tilde 1. Okay, I have this equation. And then I told you, actually, the lowest eigenfunction is non-degenerate and its eigenfunction is positive. So I know, up to a phase. So I know that phi 1, so I know the square. But phi 1 is positive, so then I know that phi 1 must be the square root of rho 1. So phi 1 I know. Of course, if I know phi 1, I know V tilde 1. Right? So you see, I find a strange thing that V tilde 1 must be the Laplace phi 1 divided by phi 1. A priori, it may not be very well defined, this guy. But I know that phi 1 doesn't vanish, and I know that V tilde 1 is nice because I assumed it. Okay? And so then this guy is complex. So you see, I have no space anymore. That's just the Laplace of square root rho divided by square root rho. So you see that the potential is an exact function of the density for bosons. So there's nothing to do. Of course, it's for fermions that we have to work a little bit before I stop. So for fermions, it's a little bit more complicated. So I have minus Laplace plus V tilde 1 uj, which is lambda j uj, with the sum lambda j equals 0. And I have minus Laplace plus V tilde 2, say uj, is uj vj, with the sum uj is 0. And I assume that the sum of uj squared is equal to the sum of the vj squared, which is rho. And I want to prove that V tilde 1 is equal to V tilde 2. That's what I want to prove. So maybe it was not so clear, but at least I also know that they are the first eigenfunctions, and so I know that U1 is strictly positive and V1 is strictly positive. That's what I wanted to tell you. I have two potentials. So then rho is also strictly positive. Okay? And now what do I do? Well, now I will follow this Oehnberg-Kohl argument. So I do the following. So first I look at the psi. So let's say the psi 1 tilde. Okay, so the psi 1 tilde is the Slater determinant, U1 tensor UN. And I know that its energy is 0. the thing. So now what I will do, I will replace V1 theta by V2 theta. So then I get here, I continue here, so I get the psi 1 theta, the sum minus Laplace plus V2 theta j psi 1 theta, and then I have plus, and then remember I get rho, and then V theta 1 minus V theta 2. And the whole thing is that this operator here is non-negative because its ground state is 0. That's what we assume here. And so this is larger than the En of the En theta of V theta, which is 0. They are not the same Ens because they are the non-interactive ones. And so I know that this whole thing is non-negative. And so you see I've proved that the integral rho V1 theta minus V2 theta is non-positive. That's what I get. But now I can do the same argument with psi 2. And then everything is reversed. So if I do the same with psi 2 theta, I will get the same with V2 theta minus V1 theta. And so the conclusion is that the integral of V2 theta minus V1 theta must be 0. That's the first thing I find. And the other thing I find is that if this is 0 here, then I have equalities everywhere. And in particular, here this guy must be 0. And so I get that the psi 1 theta is the ground state for minus that for V2 theta. And I also get that psi 2 theta is the ground state for V1 theta. So psi 1 theta is the ground state for two different Schrödinger operators. Now that sounds really strange. We are getting closer to the conclusion. Okay, so I know I have the sum of minus Laplace plus V theta 1 in x-ray of psi 1 theta is 0. And I've proved that I also have it with V2 theta. With psi 1. Okay, so in particular, I get the property that the sum of V2 theta minus V1 theta of x-ray times psi theta 1 is 0. Okay, so psi 1 is also a kind of eigenfunction for this multiplication operator. Very good. What do I do now? Well, so I want to use that. It's easy because psi is a Slater determinant. I didn't find an easy proof of this. So now I don't want to use unique continuation. So usually you say, oh, but psi theta 1 cannot vanish on a set of positive measure. So this must be 0. And then I conclude. But it's not so clear to me that Slater determinants, I mean, it must be true. But the assumptions are a bit anyway. So let me do a different proof. So what I did was just to now go to the one particle density matrix that Jan-Philippe introduced. Okay? So if you introduce the gamma, which is n, so gamma of xy is n, and then the psi of x, x2, and so forth, and then the psi of y, x2, and so forth. dx2, dxn, that's an operator, which for us is just a rank n projection. Okay, so gamma is the orthogonal projection onto u1, un if you compute. That's what Jan-Philippe said about 2 hours ago now, I don't know, some time ago, that when you compute the gamma of the Slater determinant, you get a projection. So gamma is just the sum of uj, n equal 1 to n. Okay? So what you can say from this equation with gamma very easily is that gamma commutes with this function. So maybe I give a name, so that we call f v2 theta minus v1 theta. Then you conclude that gamma commutes with f. And now it sounds really strange. Okay? So when you have a rank n projection that commutes with a function, that implies that gamma also commutes with all the functions of the functions. Okay, and it also implies that, so it says that this function stabilizes the range of gamma, if you like. Okay, so I have that, if you like, f stabilizes the span of u1 u1. And when you have a function, I have to stop very good, I'm almost done. I didn't want to replace this, but maybe I. So if you have a function that stabilizes, oh yeah, then it's better. Perfect. So if you have a function that stabilizes certain space, then any function of that function also. Okay, so I conclude, for instance, that one where f is positive also stabilizes my space, and also for the same for one where f is negative, also one where f is 0. Okay. But let me put u1 here. The guy which I know is pretty positive. So you see, I know that these three functions, they belong to the span of u1, un. So it means I have my u1, if I truncate it by multiplying by these characteristic functions, in particular, I'm still in H1. Now it sounds really strange, because this is in H1. Okay? And now from this you can easily conclude, because you have three functions, maybe I call them G1, no, this is not good, so W is not good either. I call them G1, maybe G plus, G minus, and G0. I have three functions, they have disjoint support, they are all in H1. Okay, so now when I compute the energy of U1, which is 0, which is under 1, minus Laplace plus dT gamma U1, which is just right 1 square plus dT gamma U1 square. Then if U1 is the sum of three functions in H1 disjoint support, then I know that the energy splits. Okay? So I get the sum of the energies of these three guys, but then it says that they must all be Born states. Okay, so I conclude that G plus, G minus, and G0 have to be, and because it's non-degenerate, okay, so they have to be eigenfunction for lambda 1. Okay, but now it's not possible, right, because U1 is strictly positive, and I know that it's actually non-degenerate, and all eigenfunctions have to be strictly positive, and so I conclude that two of them must vanish, and then the other one is just U1. Okay, so two must vanish. Very good. And now we are at the last step. The whole thing is, remember, I know that integral rho times f is 0. F is v theta 1 minus v theta 2. So if this guy doesn't vanish, and U1 is strictly positive, so if this guy doesn't vanish, and this guy doesn't vanish, can't be. Okay? So necessarily, I conclude that f is 0 almost everywhere, which tells you that v theta 1 is v theta 2. That's the end of the proof, and tomorrow we will change completely our point of view and we will do some convex analysis. See you. Thank you.
I wonder, what do we know in the case of Q particles, if there is some explicit expression for this ability that
No, there will be no explicit expression.
Okay, I understand that the theorem is interesting for n large, but maybe...
No, it's interesting for all n. Except, you can't quite use the same function, also the same approximations for n small and n large. But I mean, for n equals 20, they use DFT already. Or the n equals 30, which is kind of small. You know. So, and there will be no explicit, I mean, there will be explicit expressions, but of approximations of the theta, not of the full theta, which by the way we don't know if it exists.
So there are some approximations that we can, like some approximation scheme that we can.
Yes, you can summarize and say that B3 lib, for instance, is one way of computing a V theta,
Okay.
which I will explain more. And one way of computing an approximation of one V theta.
Let me ask you, I think I've asked you this before, but I forgot how you answered, so let me ask you again. So looking at these numbers of computing this water molecule, isn't it surprising that hydrophobic is actually quite good?
Because you find it good, but
It looks too good to me to be true.
no, I don't think it's that good. I mean, the question is how many digits you want to, I mean,
No, but if
graph
you
it.
have hydrophobic, you're extremely rough, it doesn't get any correlation in it, and it's off by 2% in the angle.
That's right, but I mean, if you vary the angle, so when you start at 90 degrees, you will see that the energy is also very close.